I present some aspects of AGB star wind models with a focus on two fluid flow and drift. AGB stars are rather complex objects, and it's necessary to describe all physics to realistically model the formation of a stellar wind. Here I have listed some of the things you need to account for in these models. And while this talk is more about a multi-fluid problem, here I want to stress the absolute importance of using frequency-dependent radiative transfer together with opacity data that are calculated for the molecules that are present in the stellar atmosphere. These opacity data are very rare, and it's only when I found Lars Mattsson after 15 years that I could proceed and create these or do these models, which is what our recent paper is about. So there are two such AGB star wind models that include the points of the previous slides. It's the commonly used Darwin by Höfner et al. In Uppsala. These authors use position coupling, which is a single fluid model, so no drift, and they use 100 grid points in pretty much all the models they present. Our recent T800 model includes two fluid flow, and we use 1000 grid points and more because we want to have increased numerical accuracy. Other than that, T800 includes pretty much everything that Darwin has and much more, except that Darwin has oxygen-rich chemistry, which the T800 doesn't host so far, but we're working on it. Our recent paper shows that drift velocities are significant and that the outcome is strongly dependent on drift. And this is in comparison to earlier results where drift velocities are always very small. And you see that in this middle panel here, which shows the dust mass loss rate as a function of the drift factor, which is the dust velocity divided by the gas velocity. And on the left-hand side, they're equal, and on the right-hand side, the dust velocity is greater than the gas velocity. And this gold-colored line here, it's a fit, and the fit is an exponential to the -5th power. And if that is not a strong dependence on drift, then, well, what is? Many papers observe and derive massless rates of both gas and dust. All recent studies, however, appear to ignore the drift velocity. I've listed them here. There's one exception. Nani et al. 2018 do mention drift, but they also stick to not using drift at all. And as you can see in this review of massless rates in chapter 7.1, this is from 2018, the dust velocity cannot be measured, but possibly estimated with a good enough model for the dust acceleration, and this concerns the dust circumstellar envelope. Well, this is exactly where the T800 can help, because it provides this good enough model with the dust velocities. The grain size distribution is not there yet, but it could be if there would be an interest. The drift velocity can be estimated by setting the drag force equal to the radiation pressure in the model. And this is what these two studies have done for the object IRC plus 10^216. They both derive something like 2 kilometers a second. The thing is, of course, that these two papers, they assume a stationary outflow. Our results show that stationary models give smaller effects than our time-dependent models when it comes to drift velocities and to fluid flows. And this one particular model, we have calculated set of new models for it using the T800, because this is a special object where the massless rate is higher than what we modeled before. And we calculate 2 to the 8 times 10 to minus 5 solar masses per year in these new models. And you see the drift velocity here in this panel. It is above 10 kilometers a second. So it does not go down to 0 as stationary models usually find. What does this imply? This implies that you need T800 if you want to describe the dust component in these models. And the paper is found online as are the data. Thank you.